All right. So we'll start out just kind of looking at Canvas. So I rearranged the gradebook quite a bit. I think that way it'll reflect everyone's highest and lowest. So kind of here, there's, these aren't being given kind of any weight. They're just kind of the original exams so that we have all your original answers. And then kind of had, I changed kind of how many points they were out of because there were some bonus points. Here's your Connect assignments. So they're all kind of have different questions. So it was currently kind of treating them all kind of using the points, but it's really each one's equally weighted. So it's kind of your percent grade. Here's all your online quizzes. So what I did down here, so the Connect grade, kind of each assignment, since it was a different number of points, had to kind of was just taking the average. So converted those into percentages and then kind of found what your average, what your average percent there was for your Connect grade. So that is going to be weighted 10%. Your Excel assignments, kind of the average of those is 10%. The average of your Learn Smarts are 10%. And then if we go up here, the average of kind of all your online quizzes are 10% as well. Come down here, I then kind of determined what your lowest and highest exam grade was. So I had to enter these as kind of a new assignment, since for every single person, it might not have been exam 1, it could have been exam 2. So right now I'm kind of weighting these as though they will be your best 2 exams, right? So 30 and 20%, right? That last exam, if it's your worst exam, is only 10% of the grade. But if that last exam you end up doing better than the previous 2, well, now that final would be weighted 30%, right? So there's still quite a bit of your grade that could change if that final kind of ends up being your best exam. So if you didn't do too well in the first 2 exams, this is kind of worst case scenario if you don't do well in the final. If you did well in the first 2 exams, if you got 2 100s, there's no way that your final could be better than those 2, right? So I'll kind of next week, I'll get a calculate your grade kind of tool, so that you can see like, well, if I got this on the final, what would my final grade be? If I got this, what would it be? So I'll have that next week, but I just want to kind of explain what these kind of added assignment, quote unquote, assignments are. They're just kind of different placeholders for what your lowest and highest exam score are currently, okay? Any questions on that before we kind of jump into things here? Overall, the exams were pretty good. I think there was kind of what do they call, like the economy's doing like a K recovery right now. So some things are going up, some things are going down. So I kind of saw like the middle of the distribution wasn't there as much, but the ends were. So some people did really well, some people didn't do so hot. But overall, the average was right around, the mean was around a 70 and the median was like a 75. Right? So that's usually around kind of where I want that to be. Current grades in the class, I think the average was, the mean was like a 78, 79. And I think the median was just over 80, right? So pretty good overall. You guys are doing a pretty good job, especially with everything kind of that we have to kind of compete with. But we've only got a few more weeks to kind of round this out and finish strong here. So last class, we started talking about these 2 population examples, all right? So we had our test statistic equation. We said usually the assumed true value, we're usually going to use 0. And in fact, in this class, we will always use 0. But in practice, even, we usually see 0. We also had an equation for, here it is, kind of confidence interval, right? So just like with 1 populations, we can do this in Excel, right? So we've got that 2 population HT blank file. I'll kind of show you how we could do some of this in Excel. And then after today's class, I'll post that kind of final, that next Excel assignment, right? Which will be hypothesis test and confidence intervals for 2 populations. We won't be able to get through all of it after today, but at least that kind of first portion of it. So, got this data on a bunch of different schools. It's not every school, but it's a lot of them. I've got male and female undergraduate enrollment. I've got total, and then I have kind of whether or not there was more females at the university than males. I had this separated into the South and the Midwest. So in the Midwest file, right, I kind of calculated what the sample mean, and then I had an assumed true population variance, and I calculated my sample size, right, of total undergraduate enrollment from a sample of Midwest schools. I did the same thing on the South file, but I did it for, right, the total undergraduate of these Southern schools. So maybe we want to say, are there differences I guess we could do the sample size here real quick. Do the count function, go to total undergraduate enrollment. So I might be interested in, do schools in the South tend to be larger in terms of their student body than schools in the Midwest? Right? So I've got two sample sizes. I've got two known population variances, right? This would have had to have been given to me. And then I have kind of two sample means that I calculated. Right? So if I want to do a confidence interval, right, and I go back and I look at this equation, I'll take the difference in my sample means, then I'll have to get my lower bound, I'll subtract this, my upper bound, I'll add this margin of error. But from there, it's just a matter of plugging in those two known population variances, those two sample sizes, and then finding that z-score. So I'm going to just find the z-value in a separate cell. You don't have to. You could put this all in one cell, but to kind of make it a little bit easier to see. So if we know the areas that we want in each side of the confidence interval, right? Alpha over 2 is on either side of that confidence interval. Okay? So if I know the area in the tail and I want to find the z-value that gives that to me, oops, I can type norm.s.inv. Because we have the known population variances, we know we can use that standard normal or that z distribution. So that's why it's norm.s. Tell it alpha divided by 2. Now, the only issue is if we're doing this kind of Excel, once we actually type in that kind of lower and upper bound where we subtract the margin of error to get the lower bound, add the margin of error, well, that z value we want, we just want it to be kind of the absolute value. So I can hit this, but right, if I'm just looking at alpha over 2, it's always going to be kind of on that left side. I know that I just need the z value that I can plug into that lower and upper bound equation. I need the absolute value of it, so I could use that ABS. Right? So once I do this, I copy this down, it will do it for these 3 different alpha levels, so I could build kind of 3 different confidence intervals pretty quickly. So I'll copy this down. Now I've got my z values for each one of these different confidence levels. And I kind of put a reminder here, for these different alphas, those correspond to a 90, a 95, and a 99% confidence interval. So to get that lower bound, right, I'm just going to take the difference in my sample means. Now, here I think the way I have it set up is what's the difference between the Midwest and the South. So we'll go Midwest minus the South. Actually, make sure, is it greater than 2,000? Actually, I think the way I have it set up below, no, I think it's how I have it set up. So then I'll subtract my lower bound, or sorry, to get my lower bound, the z value multiplied by the square root of each population variance divided by its sample size. But I've got 2 populations now, so I need to add in the variance for that other population, which is their population variance divided by their sample size. When I say add in their variance, sorry, the variance of the sample means for that population that I took a sample from. Okay? So it's really just getting kind of this equation entered into Excel, using Excel to find the exact z value, right? If I look this up in the table, I can find like 1.65, or even if I use that last row of the student T table, 1.645. But if I want to be real precise, right, Excel can kind of give this value to me out to a much further decimal. Now, if I copy this down, right, the issue is going to be that the only thing I want to change is the z value I'm using when I build these different confidence intervals. So I'm going to have to freeze these cells. So FN F4, or was it Command T on a Mac? And then select these. I want to freeze the population variances and the sample sizes. The only thing I don't want to freeze, though, the only thing that I want to change is this reference for where the z value is at. Okay? All right, so once I do that, now I can copy this down, and I've got my 3 lower bounds. Okay? If I want my upper bound, now if I copy this over, just using kind of my mouse, the issue is, whoa, how did I get a negative upper bound? Well, remember, it's going to update it wherever I move it. Well, I moved it over, so it's no longer using my z value. So typically, I think the easiest way to do this, and I show you this with one population, just copy this. So Control C, I'm going to copy that, enter, go over to this cell, and then you can paste it, right? Control V, okay? So it should be the exact same value, but for the upper bound, instead of subtracting that margin of error, move this out of the way so I can, there we go. I want to add that margin of error, right? But once all I have to do is change that negative sign to a positive. Now I can copy this down, and I've got my lower and upper bound here. Okay. And if I want it to be the same number of decimals, there's just a little guy up here, right? I can get them all to be maybe 3 decimals there, a little bit easier. So or even 2 if I want. Just whoops, nope. Make it a little bit cleaner, right? So you can kind of notice as we go to higher levels of confidence, our confidence interval gets quite a bit wider, right? Right, starting out, you kind of see it's fallen from 1400 all the way down to 54, okay, for our lower bound. Any questions on that, or you want to see one of those cells again? We'll work through this a little bit quickly, but we did this really with one population examples. It's just now we have a slightly longer kind of equation there for our lower and upper bound. So what can we say here, right? Well, all these values in this, even if I take the 99% level, right, 54 to like 7,700. So I'm saying that with 99% confidence, the true difference between, say, the Midwest and the South undergraduate enrollment is somewhere in this range, which they're all positive. So with 99% confidence, I can say that Midwest schools, on average, have a higher kind of student body or higher total enrollment than schools in the South. Right? Now, we're getting kind of close to 0 here, but we still are above it. So, I don't know if it'd be interesting to look and see, if I think that's the case, and maybe, I don't know, student body size is correlated with other things. Now maybe I'm interested in looking for differences in those variables between the South and the Midwest. So I thought this is kind of an interesting example. I never necessarily would have thought this or knew this, but this is set up for kind of doing some proportion stuff. So we'll scroll down a little bit here. And let's say, I have this in here, but to make it a little bit easier, for now, we're going to assume that what we want to test for is whether or not the Midwest has a higher student enrollment than the South, or that difference is greater than 0. So we'll do kind of this right-tailed test. So I have 2,000 here because I want to show you something later. So for now, whoops, we'll use this value of 0. Okay? So my alternative hypothesis is that it's greater than 0. My null is that it's less than or equal to 0. Okay? And the difference that we set up, similar to the confidence interval, is going to be the Midwest minus the South. Okay? Now, hopefully we already know what the rejection decision will be. If we look at that confidence interval, right, the only possible true values for the difference were positive. So if I'm testing for whether or not it's, if I'm assuming it's less than or equal to 0, I should end up rejecting this. Right? I should end up rejecting this null. But I'm going to kind of show you that if we go through the steps, then how we would get to that rejection decision, and then what happens if we change it to different values, right? So we've got a one-tailed, right-tailed test because there's a greater than sign in the alternative hypothesis. So I'm going to calculate my test statistic first, which that's just a matter of using Excel as a calculator. So we go down here. This was the equation that we use, right? So I'm going to enter that into Excel. So that was take the Midwest sample mean, subtract the South's sample mean, right? So that was my numerator. But also my numerator, I was subtracting the assumed true difference. Well, if it was 0, I said we can kind of ignore it. But because I want to show you what would happen, and even though I'm not going to give you examples where we don't use 0, in application, I'll show you what happens if we had something other than 0. I'm just going to subtract that 0 value that I have over in this cell, right? So even though it won't change anything because it's 0, this is kind of making sure that I'm really technically following that test statistical equation correctly. Okay. I'm then going to divide by, I believe it was the square root of each of my population variances over that group's sample size. So group 1's population variance divided by its sample size, add in group 2's population variance divided by its sample size, right? So I'm really just getting that test statistic equation entered into Excel, clicking on the cells that have the values I wanted to plug in, right? So I hit enter here. I get a test statistic of about 2.6. Right? So I'm 2.6 standard deviations away from that assumed true difference of 0. At least my sample evidence was. So when we want to find the p-value, what we're thinking about, in an eraser, is we have this distribution. We have this blue distribution, which is how are the difference in my sample means distributed? Well, we know that they're normally distributed, and they'll be normally distributed around whatever the true difference is. Well, we've assumed that the true difference is 0, right? We think about this represented the true difference. I guess we could set this up for this example, right? So Midwest and South. I converted what I saw, whatever difference that I found between my two sample means. I don't actually know what it was. We can actually check here real quick what that difference was. So 3,900 about. So we found a sample difference of about 3,908. What we're going to do is convert that into a z statistic, right? The p-value is the probability we saw something that far away from the assumed true value or something even further. Now, once I turn that into a z-stat, it's very easy to use Excel or kind of by hand use the table to figure out what that area is. So that's what we're going to try to do here. So we have that z statistic, right? We want the area to the right. Well, the norm.s.dist function, right, works just like if we were to look up this test statistic in the table. So we click on that z statistic, that test statistic, comma 1, make sure it gives us the area to the left. Now, I've said this a couple times, but I still see people making errors. If you put comma 0, it doesn't give you the area to the right. It'd be awesome if it did, but that's not what it does, right? So always put comma 1 in there, right? So it gives you the area to the left. If I want the area to the right, I simply subtract it from 1, right? And that would give me that area to the right of this test statistic, which is what I wanted for the p-value, okay? So we hit enter, so 0.004. Right? So you can think about what levels are we going to be able to reject that here? Well, is it less than 0.1? Yeah, so I can reject at the 90% level, right? Is it less than 0.05? Yeah, so I can reject at the 95% level. Is it less than 0.01? Yeah. So I can reject at all my kind of conventional levels here. Now, I could have found the critical values and kind of made my rejection decision there. So if I'm trying to find critical values, just a reminder for what we're trying to do. For critical values, I want a z value that gives me alpha in this right tail, right? So I now know the area I want in the tail, and I want to find the z-score that would give that to me. So I'm kind of working in reverse or inverse, right? So instead of that norm.s.dist, norm.s.inv. I'm now going to tell Excel the probability I want in that right tail, right? The only problem is this function works just like the table where it's thinking about the area to the left. Right? So if I wanted 0.1 in my upper right tail, there's two ways I could do this. What's one of the ways I could find kind of the z value that would give me 0.1 in the upper right tail? So instead of putting 0.1 in here, I know that I want 0.1 in the upper right tail, yeah, I have to tell Excel the area to the left, which I know has to be 0.9, right? So I can go ahead and do it that way. Or if I remember this is a symmetric distribution, if I were just to put 0.1 in, it's going to give me that same value, but negative, right? So I could just, if I remember that, I could take the absolute value. That's kind of, I won't say it's cheating, but it's not really theoretically kind of correct. So I could just do 1 minus alpha, right? That's how I got that 0.9. that would give me the correct z-value. Or if I remembered that it was a symmetric distribution, I could say, well, look, if I just put in 0.1, I'm going to get the negative value, but it's a right-tailed test. I know that I want that value, but positive, and kind of use that the absolute value function, right? Both give me the same thing. I could copy this down because it's just going to update the alpha reference, and now I've got my critical values. So if I have 1.28, 1.64, 2.32, and I think about visually, if I found those critical values, if I wanted to make a rejection decision, so 1.28, 1.64, 2.32. My rejection regions are kind of anything to the right there for this right-tailed test. My test statistic was 2.6 something, so it's going to be out here. It's in every single rejection region, which is what we said with the p-value, right? It's the same. We can reject at every single level. Okay. I'll move out of the way here for a second. So no matter which way you want to use there, you'll come up with the same rejection decisions. Now, if you wanted to do this in Excel, you could just like type in, look at the compare them and say, okay, I can reject at all these levels. But if things were to change, right, we could use that if statement, right? I'm going to just use the p-value one because I think that's easier. If my p-value is less than alpha, right, then I want to put in the word reject. Right? If it's not, then I want to put in the word fail to reject. Right? Now, when I copy this down, I want to make sure it keeps using the same p-value, so I'm going to put some dollar signs around that. Okay? So this should now automatically kind of make my rejection decision for me. Okay? Remember, when you're setting this up, remember it's the p-value has to be less than alpha. If that's true, that's what this kind of next component is, then put this word. If it's false, then we would put the other word, right? Fail to reject. Okay? Any questions on any of that before I kind of move to the next thing I want to say? Okay with that? Check the chat here. All right. So this was when we were using that assumed true difference of 0, right? Which is fine. That's all the examples that I'm going to give you. But things would change a little bit, and we could say, well, now that I know that kind of the Midwest, at least with 99% certainty, I can say that I rejected the null that it's less than or equal to 0. Right? Well, could I say that the difference that Midwest schools have more than 1,000 students on average? So this is kind of weird to think about because we've been using 0, but what I'm really saying there is the mean in the Midwest greater than the mean in the South plus 1,000, right? Or I could think about, is it 1,000 more than kind of that mean in the South? Or I could do, is it 2,000 more? I can choose any value there. Now, if I rearrange this a little bit, now I've got, is that difference more than 1,000 or more than 2,000 or whatever value I want to choose? So I can do the same test, but I can go here and say, well, actually the value I'm going to use, and I probably should just put this over in a cell here too. So what if I wanted to do 1,000? So if I wanted to say, is the difference in Midwest and Southern schools enrollments more than 1,000 students, an additional 1,000 students in the Midwest? Well, I could actually kind of reject that the difference is less than or equal to 1,000 at the 90 and 95% level, but not quite at the 99, right? With that p-value of about 0.025. Could I maybe say, well, I'm okay with rejecting things with 90% confidence, so could I say that the difference is more than 2,000? Can't say it's more than 2,000, right? Now, if we kind of think about, values that were up here, well, remember, I was actually probably can pinpoint down at the 90% level exactly what the last value I could reject is. It'd be right below this. So watch, if I put 1447 in here, that's just outside the range of the confidence interval. So I should be kind of rejecting that as a possible value, right? Because the only possible value should be in this confidence interval at the 90% level. So I'll go down here. Let's see if that's true. All right, 1447, and actually it'll be a little bit different because this is a right-tailed test. I forgot we're not doing a two-tailed test, but you can kind of see, yeah, I can actually kind of reject that as a possible value. And then as I start to creep into the values that are in this range, like when I had 2000, or let's see if 1500, I think we can probably, so we can still reject 1500. But we can kind of play around with that and figure out what's the last value that we could reject, right? Now, the confidence interval is a good guide, but the issue was it's not a perfect correlation to a right-tailed test, right? Because this was kind of thinking about looking at both sides, whereas the right-tailed test is only concerned with values on the one side, right? So if we had a two-tailed test, this would correspond exactly to what we found with the confidence interval. And I think we'll go over a two-tailed test example next week. So if I don't remember, I'm sure I will. I'll kind of make that comparison to the confidence interval and the two-tailed test when we're dealing with looks like kind of some BMI data where we're actually kind of looking at a two-tailed test next week. Okay. But for now, since we're always going to use 0, let's just change that back to 0. Okay. Any questions on that? All right, so with that all in mind, we're going to keep working through some more stuff. So let's say instead of comparing two means, we want to compare two population proportions. All right, so we can do this pretty easily. We can think about what we knew about one population was that the sample proportions, right, would be normally distributed around whatever the true population proportion was, and the variance would be equal to this. Now, the variance technically would be equal to whatever the true population proportion was, but the best we could do when we're building confidence intervals with proportions was use the sample evidence we have, because we can't observe that true population proportion. We then come down here, same thing for our second group, right? They're going to be normally distributed, these sample proportions, around whatever the true population proportion is for group 2, and the variance of our sample proportions there will be equal to this. So kind of make sure we check these, although like I said, I'll never give you examples where this doesn't hold. So what ends up being true is very similar to the means. The difference in our sample proportions is going to be centered, that distribution will be centered around whatever the true difference in population proportions is. And then the variance, right, is going to be equal to this guy. The only issue was I can't observe these, so I'm going to have to use my best estimate, which is the sample proportions that I have, right? So, we can make those, direct correlations to what we just did with sample means, right? So if I'm thinking about what my confidence interval equation should look like when I want the difference in sample proportions, before we have this equation, right? So I'll move out of the way here in just a second. And remember, this guy represented the standard deviation of the statistic that we were kind of interested in. Right? So now all it's going to be is, well, now I'm looking at the difference in my sample proportions. So I'm going to center my confidence interval around that. I'm using proportions, so just like with one population, anytime I see the word proportion, I should automatically think standard normal distribution. But now I'm going to want to multiply by the standard deviation of the statistic that I'm interested in, which is the difference in these sample proportions. Or I guess what I'm technically interested in is the difference in the population proportions, but all I have is these sample proportions, right? So what that's equal to on that slide, we'll take the sample proportion we saw from the first group times 1 minus that, divided by the sample size for that group. I'm going to run out of room, I think, a little bit here, but hopefully you can kind of, okay. And then the same thing for that second group, okay? So it's still following the same format, it's just a little bit different for proportions, because the variance, right? We're no longer given the population variance of a sample when we're dealing with means. We're going to have to know the variance of any proportion would just be that population proportion times 1 minus that population proportion. We can't observe the population proportion, so we get the best estimate by using the sample proportion we found. Okay. By the way, any questions on that? I think it's kind of easier to see when you see those two equations stacked on top of each other, but kind of a habit on this slide as well. Right? Okay, so steps are the same, right? Slightly different equations now for our lower and upper bound. With proportions, it's kind of a little bit easier because we don't have a sample mean and a variance to worry about. We just have this kind of sample proportions to worry about, and then their sample sizes. Right? Finding the z-value, same thing that we were doing before. That process doesn't change at all, right? So we don't have a whole lot of new stuff here other than kind of a slightly different lower and upper bound equation. So let's say maybe we had this data. So it goes back 2010, 2011. And it was Indiana residents. They surveyed to say, are they in favor of healthcare coverage for everyone? Right? So we've got 84% said they were in favor of that in 2011, 82% in 2010. Right? Got my two sample sizes from the 2 years. That's all I need other than what's my alpha value. Right? So if I'm looking at the 99% confidence interval, what would my alpha be? Alpha is just the area outside the interval in decimal form, so 0.01. Right? But that's not the value I look up on the table when I want to find that z-score, or that z-value, right? Because there's half of alpha on each side of my interval, so 0.01 divided by 2, 0.005. Right? So identify the piece of information I needed, those two sample proportions, those two sample sizes are alpha. We'll look up the z-score for alpha over 2. Someone I talked with, or one of you, last class was, why don't we always just use the student T when we were looking these up? And I said, I kind of agree. I think it's a lot easier, right? So when I wanted 0.01 divided by 2, so 0.005 in each side of my confidence interval, I just go down to the very last row. That would be the value I'd find from the standard normal distribution. So 2.476, almost said pint, it's Friday. You can tell what's on my mind. But from there, we just plug things in, right? And thanks for the courtesy chuckle on that. Once at this point, once I find that z-value, it's just a matter of getting things plugged into that correct equation, right? And the way we know that we need to be using this lower upper bound equation is because we're dealing with proportions, right? And they're going to be a little bit different, right? We calculate the variance for those proportions a little bit differently than we do for those sample means. But that's the only other part of this equation that's different, right? It's just that variance component. So here, I've got negative 0.03 to 0.07. This isn't a really interesting confidence interval. I shouldn't say it's not interesting, but it doesn't, what we can say here is, if it goes from, our confidence interval is going from, I think it was 0.076 and negative 0.036. The true difference, right, the change in views on covering everyone, ensuring health care for everyone, the change in that position, at least among Indiana residents, could have been a positive value, which, no, it's not a mean. What we're saying there is, right, if this difference was positive, it would mean that views have had to gone up, right? The proportion had to be higher in 2011. But if it was a negative, that could be a negative value too, based off this confidence interval, the true difference. So if it was negative, it could mean that views actually did go down, or it actually could be 0, which means that the only way the difference is 0 is if the views have remained exactly the same, right? So we can't really say a whole lot, right? We can't say they went up or down. We don't have any evidence that they've actually changed at all, right? So that's kind of how we would interpret that confidence interval. All right, what if, where are we at in time? I think I might skip this one. This is just another confidence interval example. I want to do one hypothesis testing problem with you guys today. And really, this is the exact same thing. It's just they asked a question about, do you have unfavorable views of the Affordable Health Care Act, right? So you can kind of see the changes from year to year. They're still pretty close. So once we like plug everything in, we get still negative 0.04 to 0.1. Same kind of problem we had before. We can't really say if views have went up, down, or changed, right? But if you want some extra practice, you can kind of work through this problem, make sure you can kind of replicate these answers. Right? Now I used these two as the confidence interval because I thought this was really interesting. So from this survey, notice not the change in the views isn't as interesting here, but if we just look at the level, so we had about 50% of people in both years who like didn't like the Affordable Care Act. Although one of the main components of that was ensuring, you know, the whole idea of that is to ensure healthcare coverage for everyone, but like 84% of people are behind the idea. So I thought it was always interesting, like when you look at how you ask people questions, you know, or how you package something, right? If you package it as the actual idea here, a lot of people were in favor of it. But if you package it as kind of this political Affordable Care Act or kind of Obamacare, people then were like, well, I'm not supposed to like that side, right? I'm not supposed to like that because it's their policy. So it kind of shows an interesting thing of if you actually ask people about their views as opposed to kind of these, you know, what their actual beliefs on an issue are as opposed to kind of politicizing, you might get very different responses. And there's other things in here too. I mean, this wasn't the only thing this act did, so it's much more complicated, but I thought that was kind of an interesting example. All right, so let's go to hypothesis testing, and we have something a little bit different here than we did in kind of one population examples or our two population mean examples. So we can get our sample proportions and our sample sizes, but our sample variances, or sorry, our variances for the sample proportions now, right? Before we were kind of using our best estimate. Excuse me. How can I explain this? So when we were dealing with one population examples, all we had was this assumed true proportion. So when we calculated test statistics, well, if that was the true proportion, then the variance on the distribution of our sample proportion should be equal to this, if this was the true population proportion. The issue is now that when we're looking at the differences in sample proportions, I'm not assuming that they're any level, right? The only assumption I'm making is about the difference. So remember my difference, you can kind of maybe think about it as this guy here. But let's say I assume the true difference is 0. It could be that the proportions were 0.8 and 0.8, but they could also be 0.4 and 0.4, right? So I'm not making any assumption about the actual, like where those proportions are. I'm only making an assumption about the difference. So the issue is now we don't have like say a assumed true proportion for group 1 and an assumed true proportion for group 2. We don't have those. So we have to do something a little bit different in that denominator to make sure that when we turn this into a test statistic, it's still coming from a standard normal distribution, okay? So that's kind of the motivation behind why this denominator is going to look a little bit different than simply kind of adding up these two sample proportions. Because we don't have an assumed true value for each proportion, we only have an assumed true difference. Okay? With that being said, right, it looks like it's a similar setup where I have the difference in my sample proportions minus the assumed true difference. But then I'm going to have to find first this intermediate step, which is P bar, right? So all P bar, you know, it's just, I could probably, have just plugged this in and then the denominator would look really nasty. So it's just easier to do it in intermediate steps. So I plug everything in here, get my P bar, plug that in, and then kind of there it's just a matter, you know, it's a test statistic. It's just a matter of plugging in the values that we were given in the problem. Okay? So what this denominator represents is the standard deviation of the differences in our sample proportions. So if we're thinking about kind of before with our sample means, we had this guy. This denominator represented the standard deviation of our sample difference in our sample means. When we look back at this test statistic equation, now our denominator represents the standard deviation for the difference in our sample proportions, okay? So still representing a standard deviation there, just a little bit more complicated to kind of calculate, okay? Well, other than that, all the same rules of hypothesis testing apply, right? Nothing else in terms of hypothesis testing for the difference in sample proportion changes, other than the test statistic does become a little bit more of an issue. Okay? So steps are exactly the same. Right? We've seen this, we've seen this a million times in the sense of it's going to be the same as we saw for one population. So I had this pulled. We obviously didn't get to it before the election, but it's kind of still in the not too distant past. If you look at all the polls for like political polls, yeah, I'm interested in just the statistics of it, but there was some polling data out there that had kind of 49% of people planning to vote for Biden, 47% to vote for Trump. It was a poll done, 15,000 likely voters, so people who were likely to vote. Could we have, prior to the election, kind of predicted the outcome of the popular vote? Right? It gets a little bit more complicated if we want to go like state by state and do the electoral thing, but we could actually probably predict what the popular vote, whether or not Biden was going to get more than Trump or vice versa, just based off this sample. Right? So what are the null and alternative hypotheses? Well, if I want to test for whether or not Biden will receive more votes than Trump, what I'm thinking about there is the difference in those proportions, Biden minus Trump, is that difference greater than 0? So same sort of idea. We'll still have kind of this right-tailed test. Right? We'll assume the opposite is true, which is that the difference is less than 0, so less than or equal to. Right? And from there, it's kind of exactly what we were doing before, just with a slightly more complicated test statistical equation. So it's very much like what we did in Excel earlier. Right? So what would my critical values be? Well, I'm still using the standard normal distribution. So if I want the critical value at the 1% level, right, I actually, could go back to the work that we were doing in Excel and say, what's the critical value at kind of the 1% level? Wait, why did I have, this isn't right, this is for a two-tailed test, right? There we go, that's what it should, because I have this set up as a two-tailed test. Well, that would change things a little bit. So let's say, did I do the rest of this for a two-tailed? I didn't do the p-value, so it's okay. So what I had done here, I was thinking of a right-tailed test. I was actually going to say, do they just have different votes? So let's do for a right-tailed test, why do I know these are wrong? If I really did want a right-tailed test, why do I know these are wrong? Critical value should just be positive, right? So if we were going to do this for a right-tailed test, automatically we know my critical values have to just be positive, right? I then would look up kind of just alpha, not alpha divided by 2. So it should be that same value that we found in our Excel, because we're still using standard normal distribution. It doesn't matter if we're using difference in sample means or difference in sample proportions. We're still using the same distribution, so when we look up the same alpha value, we're always going to find that same critical value. Okay? Sorry about that. I kind of switched it midway through. So what would my test statistic be, right? Well, here, this is just a point, we're at the point where it's getting used to that new equation. So what we'll first do is identify the piece of information we need. So each sample was kind of 1,500 people. We have kind of our proportions here. My Z value, right? If I was building a confidence interval, I would need that. I don't really need it here. Or if I was doing a two-tailed test, so we would have to change this to our critical value of positive 2.32. But calculating that test statistic, right? We'll first plug everything into p-bar. So I would plug in my sample sizes of 1,500, my sample proportions of 0.49, 0.47, and I get approximately 0.48 there. I then plugged in that 0.48, 1 minus 0.48, right, into p-bar here. Plug in my sample sizes, my sample proportions, my assumed true difference, which I said we're always going to be using 0 in our examples. So we get a test statistic of about 1.09. So if I wanted the p-value for this, right, I'd actually be looking for the area to the right if I'm doing a right-tailed test. Now the issue becomes like, that's going to be, well, I can kind of compare to critical values, but let's do the p-value approach here real quick. No, I don't have the Z table open. So I had a test statistic of about 1.09, right? So I go down here, 1.09. The area to the left is 0.8621, right? Well, I wanted the area to the right of that, so I subtract this from 1. So, well, 1 minus 0.8621, which is what, 0.1379. Right? So actually, you know, even with 90% confidence or an alpha of 0.1, can I reject what I assume to be true? Now, if my alternative hypothesis, remember we had the difference was greater than 0, so my null was that it was less than or equal to 0, which would mean that kind of Biden had fewer votes. Can I reject the null at this level? Well, is this less than my alpha of 0.1? Not quite. So I actually couldn't kind of reject it. I couldn't have rejected that Biden was going to get fewer votes or the same number of votes as Trump. Now, obviously, that's not what happened. So this is kind of a situation where we will make like errors, right? I should have been rejecting the null here. I should have been rejecting that Biden was going to get the same or fewer votes because, in fact, that wasn't true, right? So I failed to reject when I, in fact, should have, right? So I was making kind of a type 2 error there, right? Type 1 is when we were rejecting even though we shouldn't have been. Type 2 was if we failed to reject even though we should have been. Okay? But notice, if I wanted to give myself a little bit of leniency here, I could have rejected it at, what, 85% or an alpha of like 0.15. So it's not like terrible evidence there. It was still pretty strong evidence that went against the null. It's just if we wanted to say it with 90% confidence prior to the election, we actually couldn't have, right? And because of that, we would have made a type 2 error based off of the results that we saw. Okay? All right. Any questions on that? I know I kind of went through that a little bit quick at the end. We've got another example that I'll kind of start off Monday with. We'll work through an example by hand, and then we'll kind of do proportion stuff in Excel, right? So we should be able to get through all of that Monday. We'll then do kind of a scenario where we don't have sample variances and maybe matched pairs on Wednesday and Friday of next week, okay? All right. Have a good weekend, and I will see you guys on Monday.